do have exams. So I'll start out and just kind of look at the distribution. I think people did well. And I think, I always have two feelings when I grade. When I first grade, it's like, oh, you know, it's like I'm very reactionary. And then I grade it again and I look at it and I go, it's not that bad. And I start thinking about what it would take to clean it up. That minimum problem for a uniform was hard for a bunch of you. So that first problem, a lot of you did get it right. And those of you that got it right, I'm not talking to you. So, but a lot of people probably have thought about that problem. There's like 18 different ways to do that problem. So you could flip the bound around and then start producting through everything and say everything has to be bigger than the minimum, but you have to complement your way out of it and then recomplement your way so you get the directionality and the sign right. That's one way to do it. You could do it with the the formula of the PDF for an order statistic. Just make sure when you go from the PDF to the CDF, you know how to integrate. So, and a lot of people miss the 1 minus part out in front. So, if you gave me a negative answer for a CDF, I get a little distraught, but I also try to put myself in your shoes that you're probably nervous and just moving on real quickly is probably what happened. So if you are one of those that got caught up in that and you walked out and you're like, ouch, oh geez, good. that's about what I'm hoping for. So I honestly didn't think it was all that bad. I think sometimes we get consumed by theory and we forget how to do some simple probability problems. So I'm going to do that again and kind of like have a balance. Just as a heads up, if you got a score that you're unhappy with, you can take the midterm, write up complete solutions to the entire exam and turn them in to me in 2 weeks' time. And just show me that you know how to do it in its entirety. You missed one little problem and you want those points back, you have to do the whole exam. And it's just a repetition is good practice. So writing it all out again, I think would be a good exercise for some of you. And then some of you probably don't need to do it, but will do it anyway. So just to demonstrate, I want to make sure that everybody knows I know how to do this. And that's okay, you can turn that into. If you got 101 on the exam, you probably don't need to do anything. So there was one 101, there were several 99s. So I was pleased with that. So a lot of you didn't get caught up in it.
Are you planning on a review session tomorrow?
I don't think so. So I think let's hold off another week. Come back and do a review session next week. I've got to be at the airport tomorrow. Or actually, no, tonight. Tonight I need to be at the airport. My schedule's so all over the place.
I know that we have Steven's thing tomorrow, and there's a
That's that, yeah, exactly.
I don't know.
That's what I need to do. I need to cook a pie tonight, too. Pie day. Oh, wait. We're going to jump into minimal sufficiency. I think we'll allude to the likelihood principle today. I might give a lecture on it on Friday, and then we'll jump into ancillarity. I'll say a little bit about Bassu's theorem. You're not responsible for it in this class. I just want you to know the statement of Bassu's theorem. And then I'll tell you about complete statistics. So I'll give you one homework problem on complete statistics. Basically verifying something is complete is hard, is what I want you to see. It's not really useful as a statistician, but as a concept, I think that it's interesting to try to think about what Fisher was thinking about as he was trying to think about this whole space of statistics and what does it all mean. You might be thinking that sufficient statistics that have all the information don't overlap the space of statistics that don't have any information. And that's not necessarily true. There can be some overlap in those spaces, which is a little bit surprising. And there's a condition that tells us when those two spaces are orthogonal to each other. So I'll try to allude to that. I don't think it's the most useful thing to know about, but if you're the philosophical type, sometimes things that are interesting are just fun to think about. So it took me about 5 years to find that that concept was interesting. So, you know, there's different times in our lives where we think things are interesting. So it took me a while before I thought this isn't just ridiculous. So I can go back and forth. Still getting into the groove. Any questions about anything as we're setting? Anybody just dramatically satisfied with their midterm exam? If you are, I'm going to ask increasingly harder questions, but I'll try to allude to what they are also. So I think chapter 7 stuff is a lot of those calculations, right? You're actually doing real problems, you know, and it's not just all super conceptual. So if you like that sort of thing, I kind of do, because I know what the right answer is. It feels like a calculus problem. You'll get a chance at that sort of stuff. Random scores. So there's your midterm. This is 75, if you can't see. This is 80. This is 85. That's 90, 95, 100. So the beauty of histograms, I still can't tell what that says exactly, but I see it shoved up to the right. So just like always, I usually see some sort of bimodality in this. It's definitely not normally distributed, so I don't believe what my 3rd grade teacher told me about distributions of scores anymore. I think it was pretty anticipatable. And so I would say the people that are down here definitely pay attention to some of those easier problems that are easy to fix up, like things like the minimum. Probably that 4th problem with the regression problem gave people a few issues. So why don't I just show what that looks like real quickly. So we have a problem that looked like this. yi is equal to theta xi plus air, where this is independent, normally distributed, centered at 0, variance sigma squared, and I have given you an estimator that looks like this. Sum of the xi's, yi's, over sum of the xi's squared. There were some concerning part about algebra, and again, I'm going to just assume that it must have been nerves, very fast, you're doing it very quickly at the end, so just watch your algebra, but I do look at these steps and everything. If I want to look at whether or not this is normally distributed, I want to point out this is the random variable. So yi is the part that's random, it's controlled by that, and this is what's recentering this thing. So this is centered at that. And it has some error distribution over the top. So that's the random variable. So when I take an expectation or something like that, sum of the xi's, yi, divided by sum of the xi squared. If you do go and redefine notation for me, and it's like in the corner somewhere, and I can barely tell and it's not complete, it frustrates me when I grade because I want to give you all your points. So if you do put this into matrix notation and stuff like that, don't make me fish so long for looking for where your notation is. Again, I do understand the 50-minute thing and all of the constraints. Some of you made me search a little extra long for what you were doing. Just as good test taking, try to be as communicative as possible. So what can I I do with all of this stuff? Well, I can pull out sums of all of that. I can pull this thing out. It's just a scalar, so I can move that out. I can move that sum out. I can move these xi's out, but I can't just slide the yi out. So this is just going to be sum xi's, expectation of the yi, divided by sum of the xi squared. So this part right here is just xi theta. So if you look over at the model, that's the mean for the yi. Saw some interesting parts where sums started forming right here. So sliding some stuff in that just didn't belong there, but it's just that. So this is just sum of the xi theta over xi squared. You can factorize that thing out. So these are xi squared, so this thing is the same, but make sure all your factoring is right. This is theta. So maybe this was a test if you've ever seen a regression model before, so I presume that you have. Let's just look at it with variance. So over xi squared. Remember, variance is an expectation of something squared. So expectations of something squared, when I pull them out, all those things that I'm able to slide out get squared as well. So this is just going to look like I can pull this sum out right here. That's because of the independence that you can pull the sum out. So if I pull this xi out of the sum, it gets squared. So variance of the yi, and then I have this sum of the xi's squared, and I factorize that out, so that gets squared right there. So I try to make notes on your exam if you did something a little bit strange here. I saw a lot of people take this thing and just all of a sudden shove the epsilon I in there, which I don't have a huge problem with if you got if you get it right, but it is conceptually incorrect. So the variance of that is just the sigma squared. It's not the whole entire normal part. So your notation should help you a bit. So that's just sigma squared right here, and now I've got two of these things right here, and one of them cancels the other. So this is sum of the xi squared. I got two of those on the bottom, so I cancel out one, and this is just sigma squared, sum of the xi squared. We can come back to review session and cover all of this stuff, but I want to give you an opportunity to run through the exam and do a little bit more study if you need to. So nothing's overly difficult here, so I would say this is just a good exercise in making sure you know stuff and you know it fast. So I think that's the right time to make sure that we're up on our test taking skills, so come midterm 2, we're a little bit faster. So you'll be wanting to work problems. Again, if I touch a normal distribution or a uniform or a normal or something like that and do something simple with it, if it's in the book, it's all fair game. A lot of people ask me, can I have more practice problems? You can have a lot of them. They're in books. So go get books, read books, do the problems, and I'm not going to come up with anything that's too dramatic outside of that. So books are your friend. Last year, the year before, I had a lot of struggle with students insisting to me that books were passé. And people felt emboldened, I think because of the pandemic and internet and Wikipedia and Stack Exchange. I use all that stuff too, I think it's great. I think what sometimes happens is you get paralysis by choices. You just have too many choices. Your book is your best friend. It does not get any better than that. So books have been around for thousands of years. They will be around for thousands of years, and all of your electronic stuff will not be there anymore. But the book will still be there. So books are persistent. I do understand the flaws with books, that when somebody decides on a starting point in a book, you kind of set everything, and it's like, you probably think, well, it would have been better if you explained this part first. But you try writing a book. You know, once you're stuck with it, really you need to iterate back and forth between ideas, and so having multiple books is a good idea. that will never lead you astray. So please read your books, especially chapter 7 stuff. I'm guaranteed to grab a problem straight out of there that maybe we don't talk about explicitly. So hopefully I've made my point. Books are good. They're not passe, right? Does anybody not read books? Now you do. So, now you do. So please, go get the book, read it. If there's online versions, print it out so you can actually hold it in your hand. It'll feel more real to you. I was willing to accept the fact that I'm old and I don't know what I'm talking about, but no, we've done the experiment. What's that?
There might be issues if we try to print a 700-page book with this printer.
Yeah, that's true. There are little tiny hurdles like that. So we used to go down to Kinko's and pay for it and bind them. So that's still possible. You just don't believe that we used to do that. So I used to go and buy a book every single month, you know, because they're expensive, some of these math books. So if you have any friends that live in any other countries that have access to bootleg versions, I'm not opposed to that. You know, the only person that's missing out is the publisher. So, you know, it's the authors only get like 50 cents out of these things. So,
Dylan, are we going to get our exams back?
yeah, they got it here. I would say, based off of this, everybody can get an A in this class. So again, just be careful with what it means. Because if you're over here and you're preparing to take a qualifying exam, this doesn't look great. There's too many glaring parts of the exam that indicate you're off on some conceptual stuff. So try to clear that up and try to get over here, you know, somewhere like that. So the easy stuff that we look for. You won't get as many chances on a qualifying exam. So even though I'll give you an A in the class, if you're able to demonstrate that you know the material eventually, it's a little bit different than how I might score on a qualifying exam. Does that make sense? That is meant to scare you just a little bit because it's just such a good motivation technique. And I apologize for that. So, but it always motivated me. Okay. I would say people that are over here, just watch the easy mistakes again. Try to do a little bit of self-assessment on how bad was that. I did think that pretty much everybody's central limit theorem proof looked pretty good, you know? So you guys do know how to do that, and that's good. So some of them were a little bit harder to follow than others, but I think the gist was there. There were a few parts where people were just really quick with the remainder. So I did like the stuff where people were showing me the ratios of the remainder and showing me what goes off to 0 and not separating out those two limits, which are not really allowed to do. You can't just get rid of the remainder and then take the other limit. So if you use that sort of theory that it's a well-known fact, and I saw 3 or 4 people say that, and say what that limit converges to if the little alpha n goes to whatever, it goes to alpha, and it converges. I kind of like that. I know that it's not necessarily a well-known fact, but you say things like that, and it sounds like you understand. So you would at least be prepared to cite something. I did think people did really well on that sort of stuff. Just real quickly, what's the mean of a Cauchy? We don't know what that is, but what distribution is it? It's Cauchy 0, 1. So that's just in the book. It's buried into a paragraph. So if you knew it, that's awesome. If you wrote it down, I gave you an extra credit. Well, wow, that's cool. And if you wrote that it was normal, I'd mark you off 5 for that because the central limit theorem doesn't apply. And so that was a big ding right there. It's a lot of points for a tiny mistake. So no big deal. Again, you can collect some of those points back. If you wrote that it was like Cauchy 1 over n, I might have marked you off 1 point or something like that. so no big deal. If you said that it's a t distribution, cool. So you're right. If you didn't identify which t it was, I marked you off a point. So, cool. Some people, for the minimal order statistic, where I said, what is the CDF? Some people wrote down a sum going from k is equal to 1 all the way out to n, using that binomial representation. And if you left it like that, I marked you off a couple points, even though that it's true, because that's not really an answer. You've given it to me in this non-closed form thing, and you've used this operator, and you're regurgitating a formula. So a better answer is to write down what the actual expression of that CDF is. And so it would have been easier if you just used the complement and use k is equal to 0, so there's only one term in your sum and then 1 minus your way out of that. And so that would be a faster way to do it. Again, you could also do it by just taking that the minimum is greater than everything and doing a big product, but again, you have to complement your way out of that 2 times. You could have done some integrations. That's a way to do that problem. So start with the PDF, then integrate. Just make sure that your bounds of integration are correct. I saw some people take the PDF and they integrated between 0 and 1, and lo and behold, it integrated to 1 and everything worked out great, but 1 is not the CDF. So the CDF is a function over the entire space. So if all you needed to do was take the bound and put x in there and everything would have worked out great. So I gave you most of the points for it if you did that. So if you just wrote down the PDF and not the CDF, I probably marked you off some points there as well. So just little things that I kind of understand that it's easy to make a mistake if you're rushing. I can't quite always tell if it's a big mistake or a small mistake, so I want to give you a chance to clarify it. So again, this class isn't all about testing, it's about learning. So, and if you learn this stuff by the final and you do a really good job, I think everybody can still get an A. So there's some extra credit there. There's the Metropolis Hastings extra credit. We can go over that in review. I gave you 3 versions of that problem. The version in the homework that it says generate a t from a normal. And you'll find out it doesn't work that well. So, because you'll never really end up sampling out of the tails of the t distribution. Theoretically you will, but on a computer you won't. So just because the finite precision of the computer will never go like 20 standard deviations out of a normal. And that's not even getting anywhere, you know, for a T1 distribution. But if you end up using that random walk proposal, it'll work really nicely. So I'll give you 10 midterm points for that, entire midterm points. It doesn't rescale everybody's grade, it's just those 10 points that you'll get towards a good job. So that could be a lot, especially after you do the makeup. So I think if you do the makeup, say you get like 75, you can get 12.5 points back. So that's 87. 0.5, you get 10 more points, that's 97. So you're already there and you're covered. So easy way to make it up. If you want some 5 more points, then the 2 experimenter distribution, where you're trying to sample from that thing that looks normal S, but all of the samples sum to X bar, that's also a problem. So here's another extra credit problem where I want you to sample from this thing. This is going to look like e to the minus 1/2 xi minus x bar squared over sigma squared over n, right here. So this is not a normal distribution, so proportional to this, who cares what the normalizing constant is? If you're doing Metropolis Hastings, you don't need to know it. You can figure out what it is, but all the xi's are supposed to absolutely sum up to x bar. And so if I sampled from a normal distribution and that was mu, and I got the xi's, it would be close to mu, but it wouldn't necessarily be mu. So we can ask in a review session, how do we actually set up this sampler? And if you want to come to that review session and ask the question, I'll eventually answer your question and give you a really good proposal that works. So this was the distribution that experimenter 2 needed to sample from in the proof with respect to a normal distribution. So if they're trying to understand a normal distribution, they would have had to sample from that. So the xi's can't be any old numbers that sum up to x bar. They're concentrated somehow, and it has to do with that scaling parameter. So lots of ways you can make up some points. And I'll be happy to give you another extra credit problem if you need that. So after midterm 2. Pay close attention to your project. So bootstrap Bayes and delta method, that's going to be due in the future. So that's upcoming. So do a good job on that. I am going to grade that and look at it very carefully. So if you're somebody that doesn't do really well in test-taking environments, I'm going to make a note if you do a particularly good job on the report. A good job doesn't mean you give me 89 pages of graphs. A good job means that it's like 4 pages of stuff, that it's concise and you tell me what I need to think about. Somebody's going to come in and give me a book. So David, somebody will find a way to print out 700 pages for me. So don't do that. Don't be that person. So try to make it look nice. And if you do a good job there, I'll think, well, you're probably a really good researcher. So, which is a different skill from taking tests. I do think that that's the more important stuff, but we do need to get everybody over the hurdles of their exams. Once you're over those hurdles, it never comes back again until you're a professor and you're grading on the other side. Anybody else want to know anything else about this distribution? I mean, all the info is there, right? Anybody want to know anything, any specific numbers? Yeah, what would it all mean? You know. So anyway, I do look for breakpoints when I do end up grading. So I'm not sure what I would do with all of this. I would probably be inclined to say these are A's, something like that. Maybe there's some A minuses on the end over here. But if I do at the end of it see these big gaps in things, I'll know where to draw lines. So it's not going to be on 90. I don't think I've ever drawn the line on 90. But my lines very often could be right around here. So if there's big gaps and there's stragglers, and I look at how you collect your points. So we do make notes in the homework. If you get a 90 on your homework and you're missing, you know, there's 3 minus 3s or something like that, that's an indication that you're making a lot of mistakes that are compiling towards maybe a low performance on the exam. Good. The mean is like 89. So I don't think it means a whole lot for the distribution. Thank you for not asking. It's the first time ever. Any other questions? Cool. Enough of that. I'll hand out the exams at the end because I want you to concentrate on class. If you do get your exam and I mistotaled something, or there's a -1 or something and you just so need to talk about it, let us wait until maybe Monday for that. You can come to me calmly and say, Professor Scotland, whatever you like to call me, I think you made a mistake. And I'll say, let me look at it. So if you come to me all panicked and rushed and freaking out, you're just spending all that unnecessary energy. So we can do it calmly. Minimal sufficient statistics. Let me give you a definition that they give you in the book. Just like with sufficiency, they give you a couple ways to think about it. I'm not going to go through the proof. I find it all very obvious what it says, and I find that the proof distorts some obviousness. So I'm not going to hold you responsible for any proof here. I'm just going to give you some definitions. We're going to work through some examples. So if I give you a problem on minimal sufficiency, there will be no proof. I'll just ask you to verify a condition. So here's one definition. I don't find this to be overly useful, but a minimal sufficient statistic is a sufficient statistic. Stat that's a function of any, and that's the operative word, other sufficient statistic. Not super useful to me. So this isn't the definition I'm necessarily going to probe you with. If I do ask you for a definition and you write that down, I try not to mark off wrong answers unless you give me things in operator form. So if I ask you for an answer to something and you're like, here's the integral, you know, it's like, okay, that's true, but you need to solve it. So especially if it's like a polynomial or something like that. Let me show you an example. Let's talk about the Poisson distribution. See what we're talking about here. So I understand that I can take a sufficient statistic and take a function of it and do all kinds of weird stuff with it. It might not be the minimal sufficient statistic. So I need to be able to form that out of any other sufficient statistic. So all the sufficient statistics in the universe that you could end up writing down, it could potentially be a huge collection of them. I need to be able to transform any one of those to derive the minimal sufficient statistic. So here's the Poisson distribution. Xi is Poisson distributed. Everything in my examples are IID. If I don't say so, we've got n samples. Be very careful in all problems that I do. If I give you n and n disappears from the problem, there's a mistake there. So I did see that a couple times where it's like, where did n go? So all of a sudden you just have this thing without any n's in there. And so that's a mistake. So n's always important. So it's gotta be. So more data, something happens to the asymptotic. So Poisson distribution looks like this. So I'll just write it like this, super shorthand notation that we're maybe familiar with. This is going to be lambda to the xi e to the minus lambda over xi factorial. Let's be polite. Tell us that lambda should be greater than 0. And the xi's represent counts. So 0, 1, 2, 3, all the way off to infinity. So counting numbers. So this is your fundamental counting distribution. And we know some properties about its expectation and the variance. They're the same, they're both lambda. So all kinds of neat stuff about this distribution. There's other counting distributions out there. So negative binomial is one where you inflate the variance on things. So usually when I'm modeling and I'm using a counting distribution, I usually start with a Poisson, see if it works pretty good, build my model, look at residuals, and if they're all off or my predictive intervals or something like that is off, then I start modifying the distribution. So what would I do? I could maybe start integrating over parameters like that and changing the distribution. So those are mixture models. We'll talk about those once we get into the EM algorithm. Okay, so I could just write out the joint distribution. So the probability of x, where x is the whole sample, I probably want to write that. I just can't help myself. So I like writing out the parameter. So this looks like this. Lambda will be xi e to the minus lambda over xi factorial. And I can simplify this a little bit. I'm going to write this out a little bit differently. So this, I just get a sum up here. x3 plus x4 dot 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 of xn e to the minus n lambda. And I'll put all the factorial stuff in a product down below. So let's just review the factorization theorem real quickly. So this stuff has all my parameters in it. So this part might be my g t of x. I'll write it down more generically theta. That's lambda in our case. That's the model parameter. And maybe this thing is h of x. So keep in mind, h doesn't need to have the x's in there. It could be like a constant. Yeah, like 1 is a good example. So the uniform example is a good example of where h could be 1, or it could be like something to do with square root of 2 pi sigma, if you knew what sigma was in the first place. So h is pretty flexible, but what you're really just thinking about is where are the parameters? Obviously that has something to do with the problem. So that's squashing things down, but it's not telling us our dependence on the data. And that shows up here. So this is also important though. So that's not part of h because that has the parameter in there. But this is the important chunk. You're staring at that part. And what I do in my mind is I think about how can I express this dimensionally in the smallest possible way. And the way I've written it down, I've got n dimensions right there, and I could have left it in that format. But as we know, we could write that down as just one sum, one thing. I could break this sum up into different chunks. Like I could break that up. I could add those two things, and I could add that together. So I could have a sum of 3 things. So I could call this sum 1, sum 2, sum 3, and add those things together. Those are all sufficient statistics. The whole entire data set is a sufficient statistic. That's n-dimensional. The way I've arbitrarily written this, I can write down as S1, S2, and S3. That's 3-dimensional. So the sufficient statistic. And out of all of those things, I can form some of the xi's. I goes from 1 to n, and that's 1-dimensional. So notice that I can't take this thing right here and reformulate what those are. And I can't reformulate what the n different numbers are. But I can go the other direction. So I can take the n numbers and I can form that. I can take these 3 numbers and add them together and I can form that. So that's the idea that we're seeing here, that this is a function of all of these other sufficient statistics. So that's about the most useless definition I can think of, because that's not really the way we think about it. But really all I do when I try to recognize what a minimal sufficient statistic is I apply the factorization theorem in my head, and then I start just doing algebra in my head and seeing if I can compress things and take it down to its minimal size. And so that is what a minimal sufficient statistic is. So again, here's a definition, and it's a little eerie how you use it. So I don't think people actually derive their sufficient statistics thinking about it this way. But as we see this example, I can take all of these different sufficient statistics and formulate that thing. I can also take the sum of all of the xi's and formulate that thing. It is what it is. So A is equal to A, easiest proof in the world. So all of those different sufficient statistics I can use to formulate that. So you can imagine Fisher thinking, how do you compress the data in the smallest possible way to retain all the information? And then you can think of all these mathematical types trying to come up with a definition for that thing. So, and here it is. Okay, here's a maybe more useful. So, they don't present this as a definition. They follow this definition, and then they're also using the definition of sufficiency, and they use the factorization theorem to prove what I'm about to say, but I think that it's conceptually easy enough that we can keep it on that level. So with a grain of salt, we'll call this our new definition. It says this. So f of x, and this is some data set, and now I'm going to think a little bit more hypothetically about what this data set is. So I'm just going to let these be placeholders right here, x1 through xn, given my model parameter. If I think about another auxiliary data set, and again, these are just placeholders, y1 to yn, so they'll have the same size. This is going to be a constant. So what I mean is not a function of theta. If and only if, so this has both directions, the necessary and the sufficient condition. If that confuses you, I'll explain what I mean. If and only if t of x is equal to t of y. So this is the two data sets. Let me try to explain what I mean through this definition. So let's just take the Poisson example. And this is what I would like to see if you do an exam or something like that. You're going to verify something like this. I've talked to some really smart people that have taken this class, and they're like, how do you actually prove this stuff? Like, I don't understand like what a proof really looks like when I'm just doing algebra, and I'm like, I can't make it any smaller. You'd have to be a number theorist to come up with a full-blown real proof, and you'd be astonished at how long-winded those things could be. So we'd have to probably invoke lots of stuff about just numbers themselves. So I'm going to do this. You prove it at the level of rationality that seems to make sense to you. I understand we have a lot of engineers and practical types in this class. Let's see if we can figure out what I'm talking about. So for the Poisson example, what I'm going to look at is f of x given lambda over f of y given lambda. I probably should be calling that PR, but here's that notational difference that I've promised you all through the class. I'll just kind of shuffle through this. A lot of times I call it P or F, but I think you get the idea. So this is just going to be I goes from 1 to n, e to the minus lambda, lambda to the xi, I'll say over, we'll keep the product over here, xi factorial over product I goes from 1 to n, e to the minus lambda, lambda to the yi's divided by yi factorial. Let me just rewrite this again. It's like e to the minus n lambda, lambda x1 plus x2, so on and so forth, up to xn, divided by xi factorial, e to the minus n lambda, lambda to the yi's, sum of yi's, in a similar fashion, divided by this product. This part is not next to the parameter, so it doesn't really help us with anything. It doesn't help to tell us what the parameter actually is. So we want this thing to be a constant, and there's lots of ways we can do to make this thing a constant. So for this to be a constant, I could have all of the xi's are equal to all of the yi's. And so that means that the order would be exactly the same. So that would make this a constant if all the numbers were the same. So I'll write it like this for all I. Is what that means, but that's not necessary. So that's just a sufficient condition. So that would satisfy that, but that's not what we need for that to be true. And so I could break this up into little sums, like I did before. I could call that S1, S2, S3. I could suppose that my partition is the same, with the same indexing. So use your imagination that I've labeled that. And this is the same number of numbers right there. We have here, same here, same here. And those sums are the same. And so I can put that condition on there. And that would make this thing a constant, because everything else might be the same. So, but we don't need that in this. What we really need is we need, I'll say this is not needed. So need is a strong word. We don't need that. It would satisfy that condition. What we need is that the sum of the xi's are equal to the sum of the yi's. I goes from 1 to n. At what point are you convinced of this is really the thing. How do I prove that? And I guess I would have to go back to my very formal mathematical training and come up with some elaborate proof of this thing. That's probably why I got out of the game, where I was just kind of tired of showing things that I felt were like obvious. I'm not saying all of abstract math is obvious. Sometimes it's not at all. But in this case, it's pretty obvious. So really, what I want you to do, if you're showing that something is a minimal sufficient statistic, I want you to kind of use the factorization theorem, do some arithmetic in your head, and then write out this ratio, show me the auxiliary data points, and then make a statement and say, this is a constant if and only if something is true. And really, I'm just checking your definition. So, Sam.
So what would the non-minimal sufficient statistic look like? Like what I'm getting from this is that you would take S1 plus S2 plus S3, like these different partitions.
Yeah, but I don't even need to add them together. I could just take S1, S2, S3 in a set that's three-dimensional, and that's a sufficient statistic. Another non-minimal sufficient statistic is having all of the xi's themselves. So that's a non-minimal sufficient statistic. So it's not always the case that if you have just one parameter, that your minimal sufficient statistic will be one-dimensional, but you could already prove to yourself or convince yourself that maybe there's something out there that's one-dimensional. So, and in this case, I know that I can't compress it any further because the parameter is one-dimensional, the statistic is one-dimensional, so I'm pretty convinced already I can't go any further with this. Chris.
So this looks kind of like the proof, like when we were showing sufficiency, we did like the distribution of the test stack.
You're right.
The sample distribution. So how is this minimally sufficient?
Because we're doing this condition right here. So showing that it's a constant shows the sufficiency part. The if and only if, what's the most constraining bit of it, is the minimal part. So just showing that that ratio is a constant, whatever you've done to do that, shows that it's sufficient. So you're right, you're picking up on that first bit. It looks similar to that same criterion as we showed. Really, I was just saying that the shapes of the two functions were the same. What I was thinking was the likelihoods were the same, but that's not exactly the same condition. So it's just showing that that shape was the same and it was constant. So showing that this is a constant shows sufficiency. Making this statement that that's what we need and absolutely need, the most constraining condition for this, that's showing the minimality part.
So like, we take the sum of the yi's as the minimal sufficient statistic. That means that any function of this is also minimally.
Yeah, that's any other sufficient statistic. So for instance, all the xi's being equal to yi's, that's also a sufficient statistic, and I can form those sums out of it. Or I can take those partial sums, the S1, S2, and S3, those, and I can reform the one-dimensional sum out of that.
Could you still say then like that X bar is minimally?
Yeah, that's right. So also, we know, and you probably know by now, any one-to-one transform of a sufficient statistic is also a sufficient statistic. So X bar is also a sufficient statistic. So a one-to-one function of a sufficient statistic, and just think about it. If you have a one-to-one function of a sufficient statistic, if I give you something, and if you can map in both directions, then you can recover the sufficient statistic. So dividing by n preserves everything. It keeps it sufficient, minimal sufficient. So that's not the only minimal sufficient statistic. So there's other minimal sufficient statistics. So X bar equal Y bar is also minimal sufficient. It's because it's a one-to-one transform. Presumably, I'm going to give you what n is. That's part of the problem. Any other questions about that? Let's look at a few more examples. Let's just look at one more example, since we're at time. Let's look at the normal example. I'll do this quickly. This is in the book. Normal, mu and sigma squared. You have a problem like this. A lot of you applied the factorization theorem and were able to get through that problem real quickly. Some of you use the definition and have a little factorization problem. I just marked off a couple points if that was the case. If you were doing the right thing and all the ideas were there, it was only minus a couple. So if you communicated well, I stopped here. It was going to work out. I just got lost in my factorization. That was okay. That's like a -3. Okay, so for the normal example, I might look at something like this. Mu and sigma squared divided by f of y. Given mu and sigma squared, I could write this out in the full-blown glory using the product form. I'm just going to shortcut this a little bit just because we all know this stuff. And we've seen this factorization many, many times. Sigma squared minus n over 2. 2 pi sigma squared minus n over 2. That's coming out of the product. And I can write out some terms. This is e to the minus 1/2 sum of the xi's minus x bar squared over sigma squared. E to the minus 1/2 sum of the x bar minus mu squared over sigma squared. I'll do something similar. Y bar minus mu squared over sigma squared. So I could have worked in the product form, had that quadratic term, added and subtracted x bar in there, factorized things out, looked at the cross term. The cross term doesn't go to 0, his n goes to infinity. I saw that twice on the midterm. It's just straight up 0. So the cross term. So try to convince yourself of that, and I can break this up into a couple different terms. Already we see some interesting stuff if you're able to apply the factorization and theorem in your head. I know what's sufficient for sigma squared because I can't untangle that. And I can't untangle x bar from that either. And so, but this is the sort of thing that you might be able to rationalize and say, this is a constant if and only if this thing right here is equal to that, and this thing is equal to that. How do you prove that? Number theory. We have to go way back and take a lot of advanced mathematics classes, maybe to prove that fold. But I think we can kind of see there's two parameters here. I've got this two-dimensional thing, and I could at least convince somebody on a test that I've done the factorization, I know what the sufficient statistics are, and I can make a statement that if sum of the x bar minus mu squared is equal to sum of y bar minus mu squared, and sum of the xi's minus x bar squared is equal to the sum of the yi's minus y bar squared. If those are equal to each other, this thing is a constant, and I can't compress that any further. So how do I know that? Because you can just try forever and keep trying to compress that, and you'll never compress it to conditions that are different from these. If you ended up saying that the first and the second moment need to match each other or something like that, you would be right with that analysis as well, but it would be equivalent to this. What we don't need for this to be a constant is all of the xi's and the yi's to match. I'll point out as an example, a Cauchy or a t-distribution, you can never end up compressing those sufficient statistics. So for a Cauchy distribution, which is a scale and location family, all of those little data points, the devious ones, really matter. And so we really need to know the individual data points. So, and that's where we get to the answer from the solution manual when they're talking about a location scale family, that they say that the order statistics need to match each other. So for a Cauchy example, everything looks like this. They have this in the book as well. This is going to be 1 plus xi's minus theta squared to the minus 1 product. I goes from 1 to n. Product I goes from 1 to n, 1 plus yi's minus theta squared to the minus 1. We need this thing to be a constant, and we might be thinking to ourselves, how do I end up factorizing this in some really neat way that I can compress everything? And you can try all you want, but it'll never actually work. So you won't be able to compress the dimensionality of that sufficient statistic. How do you prove that? I think the book even says we need more advanced classes in mathematics to convince ourselves that you can't compress this any further. We don't actually need the yi's and the xi's to match up. What we need is the order statistics to match up. And that's because I can shuffle the yi's and the xi's in any order, and the products will still be the same. So that's at least some insight on that problem you've already worked through that I think you're going to turn into soon. But I assume you worked through that problem. So this would be a good example of when the order statistics are the sufficient thing. And it's just a statement about the IID nature of the data and it's exchangeable. So here's just some examples. All I want you to do on a test is be able to write out these ratios. If I ask you to verify something is minimally sufficient, it's pretty easy to do. You're just going to chisel away at those ratios and put them into a compact form that involve those two statistics. I didn't ask that on midterm 1. So, but if I had asked minimal sufficiency, you would have just taken that S squared term and formulated that thing, and you would have used the mean term to formulate this. And then you would convince yourself, or at least write down, this is a constant if and only if these two conditions are true. So I don't want to get too caught up in the weeds of what an actual number theory proof looks like, because I'm not sure that I can actually do it myself. So somebody might not be satisfied. I've probably convinced most of you, but there's always another level that says that proof's not good enough. Okay, so it's not meant to be a super difficult concept. Let me just say it a different way. A minimal sufficient statistic is a sufficient statistic that you cannot compress dimensionally any further. So maybe that's the best definition. Okay, we'll come back. I would like to talk about, I think, the likelihood principle before we jump into ancillarity, so a slight adjustment to the order of everything. And then next week we'll be getting into ancillarity. Mohammed has homeworks to return to you, and I have exams, so I'll call your name and just throw your hands up. Zach?